Hello and welcome to the Advent of Code, day 14, part 2. Now we have some pain, because as I actually was worrying about in part 1, the part 2 is asking us to go forward of 40 steps, not 10. And then essentially we have to do the same operation that we did in part 1, but with 40 steps instead of 10. Now, this number 10 is simply a parameter that we have in this where is it, in part 1. So here I can put just 40 instead of 11, but this won't work. In fact, we can try it immediately, and you will see that where is it? Here. Sorry, wrong code. Because meanwhile between the videos I committed the code. So this will basically hang at some point, for the simple reason that every time we run a step, we double the size of the chain. This is by definition. Every time we insert elements in the middle, if we had 10 elements, we had 9. If we have 100 elements, we had 99. Which means that the size doubles, pretty much. There is one of difference, but still it doubles. Which means that the amount of elements will grow exponentially. And the ugly thing of exponential growth is that well, exponential. So at 40 steps, we will have 2 to the power of 40 elements, at least of order of magnitude. How much is 2 to the power of 40? Is a lot. That's the short answer. So 2 to the power of 10 is 1024. 2 to the power of 20 is 1024 squared, which is around the order of magnitude of millions, which is still doable, to be fair. But if we have 2 to the power of 40, it will be 1 million square, which is a lot, is 1000 billions, so it's quite a lot. It's not very feasible. So we need to find some smarter representation, some way to not store in memory the whole polymer, because it's not doable, it will be too large. You can see also from the sample solution for sample problem that this number is just too large to not the number itself, but an array, a list of this size is just too large. So we need something smarter here. And it's easy to do, because we actually found a similar problem in the previous days when we had the fishes that multiply. In fact, it was a similar idea. We have a list of fishes and a population with some ages. And instead of keeping the list of fishes, which is undoable, we keep the count of them. And we have to do the same. We have to keep the count of the couples. So let's try to reformulate the problems in terms of couples and see what happens. So what we're going to do is first we solve again the problem for 11 steps. The solution is 2745. I remove this print that doesn't do anything useful now. 2745. So what I do is, to make my life simpler, I put here an assertion. Assert part 1, sorry, let's say solution 1 is equal to the solution of part 1. I print it, and then I assert that solution 1 is equal to 2745. Why I do that is just a simple way to have a sort of test inside my own program without writing an actual test that will take forever. And I can now try to change the way the problem works, but still check easily that the solution 1 is the same. So this is an easy way to check that the result is the same. So what do we do? The solution is simple. In the polymer will not anymore be the string that defines the whole polymer, because that's unfeasible, but a dictionary that counts how many couples are in there. So the polymer here will not be anymore a string, that's not doable, but instead it will be a dictionary. So how do we transform the polymer into a dictionary? We have to do something like this. We have, first of all, the polymer is, let's say, ABC. It will become a dictionary like this. AB is a appearing 1, BC is appearing 1. If we had something like ABC, AB, then we will also have CA that appears 1, and AB is repeated, so appears twice. So essentially we have a count, a dictionary that counts how many consecutive letters are there. Notice that we count AB, but then also BC, so every couple of consecutive letters. At this point, calculating the reactions means to go to the dictionary, find every possible reactions, and add them back to the original dictionary. So, let's see how do we represent the polymer now. We have a polymer which is line strip, okay, fine, but let's call it polymer string here. So polymer will be a dictionary now. Polymer string is this thing. We have to go through all the letters that are in this polymer. So you know already how to do that because we have the zip function. So we say for A, B in zip of polymer string and polymer string starting by 1, we increase the polymer of 1 for that couple. So polymer of A plus B will be equal to what? To the polymer of A plus B plus 1. But this polymer A plus B could just not be there, so we have to replace these square brackets with a dot get A plus B 0. This is something we saw in the previous problems. When you want to create a count of the sequences in the polymer, you have or the sequences in a dictionary, you have to use get that is equivalent to the square brackets if there is an element, but also allows you to define a value to get when there is nothing. So this get simply say, okay, get me the element with the key A plus B. If there isn't, give me 0. Then you add 1, so if there was one element, you just increase it by 1. If there wasn't, you just get 0 and increase by 1, so you get 1, and you put it back into the polymer. So polymer now will be a dictionary of counts, and in fact we can just print it. So print polymer, and we see what happens here. Now, of course, the solution 1 doesn't work because it receives a dictionary now instead of a string, but it's fine. Let's see. This was my day 14, and the polymer seems to be working. FP appears once, OB appears once, so it's taking the start and the end, which is correct. And F appears too, so here and here, that's correct. Okay, it's working. So the polymer is working. This is the polymer. Now what do we do in the part 1? We get a polymer, and we get the reaction step. Okay, reaction step is where the reaction happens, of course, and here we have to do some trickery. So first of all, we have to go through all the elements in the polymer. So we say that for couple and count in polymer.items, what we get here is a couple, which is something like I don't know, AA, and a count, which is just how many times it happens. So we say, okay, let's get an insertion. So insertion is equal to reactions for the couple. And now what we do is we say, okay, let's say that there were 23 AB, and we know that AB becomes, let's say, R. What we're getting now, this is the input, so this is the element in the polymer, this is the element in the reactions. We have to combine them, and we calculate that there will be AR that happens 23 times and RB that appears 23 times. So this is the input and this is the output. Since we only care about the count, we don't not care about the real structure of the polymer. This is essentially calculating a very smart and shortened version of the same result. So we have to simply create a new dictionary. So new polymer, I call it. New polymer will be a dictionary, initially empty. And here I say, okay, look, insert into new polymer the two new couples that are generated by this operation. So new polymer for couple 0 plus the insertion is just a letter, will be equal to what? To this thing again. So to new polymer, but this time we do get again same pattern as before. Otherwise 0 plus what? Plus the count. So essentially we take the number of times this thing was in there and increase it by it. And same we do for the other couple. So insertion plus couple 1. So we are taking the two new couples of letters that are generated by inserting this extra letter in the middle, and we are simply taking the frequency of it. I can format the code a bit. Okay. So example. Input, we had a couple, a B that is 23 times. So we say that in polymer we have this thing. In reactions we have AB becomes R. Result, we say that AR 23 and RB 23. And they are added to the complete count. So the new polymer will contain the new count. The whole code is gone. We only return the new polymer. New polymer, okay. And this should be it. The complexity is not really changed. Polymer is a dictionary now. And reactions is also a dictionary. And that's it. So let's see what happens now. 1179. Yes, also there is a problem that in part 1, so let's print the steps. I want to check that this is actually still valid. Let's get the original value, the one in the problem, so that I can see immediately if there is some trivial error. Wait, let me rename this thing. So original, I don't want to copy paste every time, so I just create two files with similar names. day14.txt, I copy this thing and run the code, this time printing the result. So let's see that it is actually working. At step 1 we had this thing nc blah blah hb, so nc blah blah hb, everything happens once. At step 2 we have nb that appears twice. No. nb, okay, seems to be correct. And step 10 we have this thing. This seems correct. But now we have a small problem, which is that here we have the couples, but what we care about is the count. Is how many, we want to know how many times every couple is appearing here. So what do we do? How do we calculate the frequency? It's not anymore such a simple function, because now we have all the couples, and a letter can appear in the first and second element. So what we do, let's create a new function. We call it count component. There is no, it doesn't give us a name for the letter, so we say just count letters. For the polymer is a dictionary. This will give us another dictionary, which will be the count of every letter. How do we do this? So we have letters, which is going to be a dictionary, which is going to be the, let's call it counts. And then we iterate over all the tuples, or the couples. So for couple count in polymer.items, I say that counts for, what is it, the starting letter. So counts for couple 0 is equal to the same thing. Oh, I pressed something by mistake. Yeah, is equal. What happens? Okay, is equal to the same thing. Again, we have this 0 trick plus count, and then we return the counts. So essentially, for every couple that we have in the dictionary, we count how many times that letter is at the beginning of the pair. So for example, this H is here, but also here. We need to count only one of them, because otherwise we double the elements. So in part 1, we now do what? We get this stuff, count the letters of polymer, and I print them. So I run the solution again. This is wrong, I don't care. I want just the count of the frequency. Okay, so this is, I ignore it. So this is the solution, sorry. This is the solution, and blah blah blah. So we have D, for example, that was going to appear 1749 times. And you have it here. It's not yet correct, but we'll fix it. 1749 times and 161. Why is it 1748 times? Because we because B is at the end. So we have a last couple that is not going to be anywhere. So essentially, this B is counted as part of CB, but not a part of something that is after this. So what we do, we can add a terminator. So when we count a polymer, we will have a special letter, which will be the last one. And that letter has no effect, is not part of any reaction, it's just a way to mark the last element. So when we parse, we already add a terminator here. We call it 0, is the number 0, so it never appears here. And this 0 has no effect anywhere, because there is no reaction with the 0. So if we run, we should get an error, because B0 doesn't exist. But that's expected. So what we say is, okay, look, when couple ends with 0, so if the second element is at 0, then you simply put the couple back inside the insertion. So insertion of new polymer of the couple is 1. Why can we do that? Because we know that there is only one and only one terminator, so we do not have to do any reasoning like get and increase the count. It's 1. It just stays there. So if I run again, And I continue because I do not want to calculate any insertion. I know that this is a sort of fake couple, so I just want to preserve it. Okay, and now the count is correct. We have B, which is 1749, H, that is 161, and that is 865. So these are the counts that we had here. And this can be now reworked into a count. So we have a dictionary with the counts, and we want to get the max and minimum value. How do we do that? Is trivial, because frequency ranking is this dictionary. We want to get the highest and lowest value. So what we do is we return freq ranking dot values. We take the max, values, and we take the max of it minus freq rank. Or let's just do something even easier. We take the list of the values of this directly, because we do not care at all about anything but the counts. We don't care about which letter. We just care about the count. So now freq ranking is actually freaks, so the list of frequencies, and the result is the max and the min. So the maximum frequency minus the minimum frequency. Let's see that it works. Okay, so this is not really working. Why? This was actually a very good solution. Seems to be it worked. We saw the thing before. Let's see again. So we have to take the maximum minus the minimum, right? So 1749 minus 161, 1588. I'm stupid. I'm I'm using the sample solution and comparing it with my expected result. So okay, so let's do something simple. Okay, that this kind of stuff happens all the time. So this is it was correct. So this is the sample, and this is the original. So I take my original, and now if I run again, I should get a result. Thank you. Okay, this is the result. There are no essential errors, which means that we actually got the solution. And now we can simply run the part 2. Part 2 will be exactly the same, but for 41 steps. So I run. Okay, I didn't pass the values, so I didn't pass the arguments. Okay, and this is the solution to our problem. That's it. Thank you for watching. Let's see a few things about this code. So the first is that there is some duplication. Part 1 and part 2 are identical except this number. So the logic could be moved to a function that then is called by the two, which is probably what I will do, but not in the video. It's just a trivial change at this point. The key for this is to always think about what we have to do with the data structure. We do not need to use the list. We don't care about the list. We care about how many times a specific couple appears in this list. So a dictionary with the counts is actually a best representation. We can have 1 million elements for every letter, but in the end the possible couples are very few. So the key to solve this problem is to think about what are we going to do with the value, and that's how you choose the data structure. So thank you for watching. Hope you enjoyed the video. I will publish the code on GitHub soon, and see you tomorrow. Bye.